We're going to conclude our discussion on the electric field by talking about Gauss's law. Gauss's law is a principle in electrostatics that describes the amount of electric field that actually passes through any surface or any object. So to discuss this, first we need to talk about electric flux. The electric flux is a measure of how much electric field passes through some area A. So the way we calculate this electric flux is we indicate it with this. This is the Greek letter phi. So electric flux, phi sub E, is going to be the component of the electric field that is perpendicular to a surface area A. So look at figure A. This is what we're dealing with. An electric field is moving to the right, and you have some area that's tilted. Well, the first thing we're going to do is draw a line that is perpendicular to the surface area itself. Okay? And then we're going to measure that angle between that perpendicular line and the electric field itself. Why? Well, if you look at figure B, basically what we're doing is taking our electric field and then taking our line that's perpendicular and then draw a component, basically make a right triangle out of this. Then you're going to have a part of the electric field. Let me draw these in different colors. So you end up with a part of the electric field that is perpendicular to the surface area A, and a component of the electric field that is parallel to the surface A. So you have your surface area that goes this way. This parallel component goes in the same direction. We don't care about that perpendicular component because with electric flux we're talking about how much electric field passes through the surface. So we want the perpendicular component. Now, following trig, so there's our vector E. This is a right angle. Here's our parallel component. Here's our perpendicular component. So this is your hypotenuse, and this is your angle theta. The perpendicular component is the side that's adjacent to your angle theta, and adjacent means cosine. So the adjacent side would be the perpendicular component divided by the total electric field. So the perpendicular component would be E cosine theta. So if we take that and we plug that in here, then we end up with this equation for the electric flux, that the electric flux is going to equal the magnitude of the electric field times the surface area times the cosine of the angle between the two. Okay, with that in mind, we're ready to talk about Gauss's law. Let's say that you have an object and you have an electric field that is passing through it. We are interested in how much electric field passes through a certain given area. So we're going to take this surface and divide it into small areas. We're going to call them A1, A2, A3, A4, A5, and so on. You can imagine we'd have practically an infinite number of these. But we're just going to do a couple just to find it out. So the electric field that passes through the surface area 1 would be E1 A1 times the cosine of the angle between them. Around A2, it would be E2 A2 times the cosine of the angle between them, and so on for each of the areas. And we just add them up. Now, to do this properly, you're going to need something in calculus called an integral. We're not going to deal with the integral. We are satisfied with just approximating it as the sum of perpendicular electric field times area for each area on our surface. Okay? Now, let me give you a simpler example. A cube. You get an electric field that passes outside of each area. And it looks something like this. Every surface, there is an electric field of equal magnitude coming out. Okay. In that case, then the electric flux would be the sum of EA cosine of, well, since it's coming straight out, these electric fields are perfectly perpendicular to the surface. But remember, we don't measure that as 90 degrees. We have to measure that from a line that is perpendicular to the surface, which means the electric field and this line perpendicular to the surface are in the same direction. Therefore, that needs to be 0 degrees. That's important because cosine of 0 is 1. If we did cosine of 90, we'd get 0. That'd be a problem. So in this case, the electric flux then would be the sum of the electric fields times the areas. Well, the electric field is the same through all sides. The area is the same on all sides. So that would, and there are 6 sides, so that'll just be 6 times the electric field times the area, whatever that is. So there's a quick, simple example of calculating electric flux. With that in mind, we're ready to talk about Gauss's law. Gauss's law tells us that the net number of field lines that passes through a surface is proportional to the charge that's enclosed, and thus also proportional to the flux. In fact, here, this is our electric flux. It's going to be the sum of our E perpendiculars times A. Gauss's law says that that value is equal to whatever charge is inside our surface times epsilon, or divided by epsilon naught, which epsilon naught we saw earlier. That was 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. What on earth is this saying? Well, let's go back to the example we just barely finished. There's a cube with an electric field passing through all 6 surfaces. Well, we found that the total electric flux was equal to 6 times EA, where E is the strength of the electric field passing through each surface, and A is the size of each side, the surface area of each side. Well, that tells us, well, first of all, that those electric fields, the electric field lines, had to come from somewhere. Since they're all pointing away, that tells us that there is some positive charge Q embedded in the middle of this box. And according to Gauss's law, the electric flux, 6EA, has to be equal to that positive charge that's inside the box divided by the constant epsilon naught. And that's what Gauss's law is telling us. It's relating it's relating the charge inside of a surface to the amount of electric field that passes through that surface as well.